Hello, students. Today we are going to start a new chapter, which is thermodynamics. So, in this chapter, we will have several objectives, and basically, this chapter consists of multiple layers. So, you will understand one by one how this chapter is relevant to your class 11 teaching program, and we will step by step, very slowly, but very in a very lucid manner, we will know what is thermodynamics, what is meant by this term, and why is it so much important to have a discussion on this chapter. So before going to take a plunge, I would like to let you know that this chapter is very vast. It has multiple layers. So you have to understand each and every point that I am going to tell you, and I'll emphasize on those aspects which you need to understand much more. So with this, I will start with a very brief introduction on thermodynamics. So before going to this term of thermodynamics, I'll first start with the basic thermodynamic law. So what are the laws of thermodynamics? Which are the general aspects that I will share with you? So first, let me start with some basic things. You see, when a chemical reaction it is going on, a chemical energy is actually stored in the molecules. You see, suppose these are some molecules. These are some molecules which we have in number of molecules, and a chemical reaction that is currently going on is actually a heat-like reaction. You can assume that a cooking of gas is actually going on. So suppose this is a container, and in this container we have some n number of molecules. These are this n number of molecules, and they are actually being heated. So there is a kind of cooking gas. So here the fire is there, which is supplying heat energy, and these molecules here inside the container are getting excited. So now in this case, what we can see, a chemical energy is actually stored by the molecules, and they can be released as heat during the process. Just like when we actually burn a fuel like methane gas. You might have known about this gas, which is methane, which is combustible, that easily it catches fire. It is a methane gas, CH4. It is the simplest hydrocarbon which can be actually used like a fuel. Or another example I gave you, like this cooking gas. Or else you can think about coal that is actually burnt in air. You know, previously in trains or in trams, coal was used as one of the fuel sources. Now, this chemical energy that is actually stored in the molecules, the energy is actually designed by the letter E, which stands for energy or chemical energy. So the chemical energy that are we are actually talking about, it can actually be used to perform some mechanical work. Now, mechanical work means what? When a fuel is actually burning, you know the engine actually runs. So when fuel burns, when there is a fuel and when it burns, we actually get some mechanical energy. Mechanical means where a mechanics kind of things are going on. So something is moving, or something is going forward, or something is coming backward. These are actually called mechanical terms. So when the chemical energy is actually used to perform some mechanical aspects, these are some examples, or the electrical energy that is also very trivial in galvanic cell. So in this case, you see, if we take out this kind of thing, and we actually get to know that the chemical energy that is stored inside a molecule can be turned into some mechanical work or electrical energy work, like the galvanic cell and the dry cell. So in such cases, we would actually come up with the term of chemical energy being transformed to several different kind of energy, like mechanical energy or electrical energy. So if we have this chemical energy, and this chemical energy can be transformed to many different kind of energies. The first one is obviously the electrical energy, that is actually very much trivial in case of galvanic cell like dry cell. Or in case it is kind of mechanical energy like running of trains or running of engines, this kind of energies. So from this basic introduction of chemical energy getting converted to mechanical energy or electrical energy or various other forms of energy, we can have an idea that a various kind of or forms of energies are interrelated. They can be interconverted under different certain conditions. So depending upon which condition we are actually applying, a single form of energy can be transformed to various different kinds of energies, electrical energies, mechanical energies, and whatnot. And these may be actually transformation of one energy to another is the basic law of thermodynamics. So what we are actually learning from this chapter. So before going to the depth of the chapter, this is a very brief introduction to the thermodynamics term, like what it is getting originating from. The origin is when a certain amount of energy is getting transformed to different forms of energy, and the energy cannot be created or destroyed. It is fixed, be it electrical, be it mechanical, or different other forms of energy. The study of all these energy transformations, this is the subject matter of thermodynamics. So in thermodynamics, you get to see like we are having different kinds of gases, different kinds of things, and every kind of their things are actually going on. And if we are again coming back to our main cause, like what we are going through do in this chapter, we will actually study the different laws of thermodynamics, the different thermodynamic terms and parameters that will be very much helpful for us to get a very good idea about what the chapter is actually looking for. Now, in thermodynamics, there are different kinds of law, and in one by one scenario, I'll get you to this journey. So if we come to the very first law of the thermodynamics, like what is the basis? You see, this is the first law. In this law, you see there you will get to know there are different laws of thermodynamics, like the law one, law two, and law three. But before going to what these laws are, we will first know some general aspects. So here I actually merged all the general aspects of thermodynamics to give you a clear cut idea. So, firstly, it will deal with the energy changes of the macroscopic systems. Macroscopic systems are those which are actually involving very large number of molecules. So, the number of molecule that is capital N is very much high for macroscopic systems. But in case of microscopic systems, which are having very few molecules, in this case, they are actually not considered in thermodynamic world. So let me have a bit of glimpse over here. In this case, we have two kinds of system. One is the macroscopic system and one other is the microscopic system. In thermodynamics, we actually study about the macroscopic systems, not the microscopic systems. In microscopic systems, there are actually large number of molecules. So number of molecules which is actually denoted by capital N is currently very high. But in case of macroscopic systems, the number of molecules is small n. And for any instance, capital N is very, very large than small n. So in macroscopic systems which are having very large number of molecules, that is capital N, and in microscopic systems we have very few number of molecules, which is small n. In thermodynamics, we are actually dealing with the macroscopic systems, not with the microscopic ones. Thermodynamics is not at all considered about how and at what rate these energy transformations are carried out. So previously, I have given you an idea that in thermodynamics, the basic thing that we discuss or we are actually looking into is the energy transformation. Energy forms are interrelated between one another, and their forms can be transformed from electrical energy to mechanical energy to different other modes of energy. And in this case, the thermodynamics is actually even bothered about how these energy transformations are carried out. So two things thermodynamics is not actually bothered about. The first one is the how or the process. Thermodynamics is independent about the process, like in what procedure the energy transformations are being carried out. And secondly, the rate, the kinetic rate. Thermodynamics does not take consideration of these two parameters. First one is the how parameter, that is the process, and second one is that what rate these energy transformations are carried out. Then the trivial questions of the very available question, first one that is coming up into any student's mind is what it is actually based upon. It's based upon the initial and the final state of the system that is undergoing any change. Suppose we have a system which is denoted by A, and if we are actually trying to see how this system is undergoing to change, we will take its final state, that is A final, and we will take its initial state, which is A initial. So between AF and AI, the difference that is the system is undergoing, that is actually getting concerned about thermodynamics. So thermodynamics does not actually care about the process. It does not care about the rate at which the energy transformations are getting carried out. But it depends on this A final, that is the final state, and A initial, that is the initial state of the system which is undergoing the change. Now, the first very two general aspects are hereby cleared. First one is the macroscopic system versus the microscopic system. Thermodynamics is concerned about the deal of energy change of macroscopic systems, not the microscopic systems. And secondly, it does not actually care about or does not get concerned about the rate at which these energy transformations are carried out, but only the initial and the final step of the system. If we come to the third aspect, which is the equilibrium concept of thermodynamics. So in thermodynamics, the laws will get applied only when a system is in equilibrium or it moves from one equilibrium state to another equilibrium state. If I have to explain this situation, let me come up with a example. When we have a system which is noted by S, and this system is S suffix A is actually in an equilibrium with another system called B. So for systems, two systems, we are having SA and SP. SA and SB are actually in thermodynamic equilibrium. So the laws of thermodynamics will only apply when the equilibrium is getting remained. Or you can say, like from SA is actually getting in equilibrium in SB, and it is moving to some other equilibrium system, which is denoted as DA is in equilibrium with DB. So we have firstly equilibrium denoted as SA and SB. And now, after some changes, a new equilibrium is going to get reached, which I am denoting as dA in equilibrium with dB. The laws of thermodynamics will be applied only when a system is in equilibrium or it moves from one equilibrium state to another. So this was the equilibrium number one, and this is the equilibrium number two. So when any of these equilibrium 1 or 2 is reached, or any interconversion between equilibrium 1 and equilibrium 2 is going on, then only we can say the laws of thermodynamics can be applied. So here we have discussed the first three major general aspects of thermodynamics. So you will see, like the fourth case, here it is actually mentioned over here. In the fourth case, you can see the macroscopic properties like pressure and temperature do not change with time for a system in equilibrium state. So if I have to explain this point, we have some macroscopic properties like pressure of the system, temperature of the system, volume of the system, etc. Now, in equilibrium state, the macroscopic properties like this pressure or like this temperature, these actually do not change with time. So these are actually independent of time in equilibrium state. So when an equilibrium is reached, in equilibrium with time, this system, these conditions or the properties, they are actually not changing. So in this unit, we will like to clarify or like to answer some of the very important questions that we will need throughout the thermodynamics. So how first one is the how to use or how to determine the energy changes that is involved in a chemical reaction or chemical process. Will it occur or whether occur or not? That is actually another question. So firstly, we will determine the energy changes. Energy changes. And now we will see or we will try to look into the fact like what drives a chemical reaction or process. Or so we will get to know whether a chemical reaction is proceeding or not. How will we predict a chemical reaction whether it is going to take place or not? So what actually is basically driving the chemical reaction? And lastly, to what extents do the chemical reactions proceed? So we will know the extent of reaction, like to what extent the chemical reactions will proceed. And finally, we will get to know what is actually driving force behind the chemical reaction or process. So three questions are actually very basic over here. First one is the how will you determine the energy changes that is involved in a chemical reaction or process? Secondly, what is the extent of the chemical reaction that is going to undergo? And lastly, what is the driving force behind a chemical reaction? So now, when we have got through the laws of thermodynamics with some general aspects, which we will again repeat on a basic note to give you a clear-cut idea. First one is the macroscopic systems are actually involved in thermodynamics. Thermodynamics does not pay heed to microscopic systems. Secondly, thermodynamics is not bothered about how and at what rate these energy transformations are carried out, but it is based on the final and the initial states of the system that is undergoing the change. Thirdly, the laws of thermodynamics apply only when an equilibrium is reached or there is a movement from one equilibrium state to another. And lastly, the macroscopic properties like pressure and temperature, these do not change with time for a system in equilibrium state. They remain constant. Now we will move to our next slide where we will see some of the basic thermodynamic terms. So we are actually interested in chemical reactions and the energy changes that are actually accompanying them. And to have a clear cut idea about this entire scenario, we first need to know some thermodynamic terms. So these are the thermodynamic terms that we will first need to know, that these terms will help us to understand the chemical reaction and the consequent energy changing processes. The firstly is the system and the surroundings. Here you can see the system and surroundings. A system in thermodynamics, as you can see over here, refers to that part of the universe in which the observations are actually getting carried out, and the remaining universe constitutes the surroundings. The surroundings include everything other than the system. So the system and the surroundings together constitute the universe. So let us assume with a very classical example, like you can see, this is the universe is actually getting consisted of the system and the surroundings. So suppose if you have to understand this system and the surroundings process and the total universe process to very well, you can take up a system like you are having a glass of water in your home. So this is the glass of water which is actually kept on a table. A glass of water is kept on a table, and you see there is your home, your house, or everything over there. Now, if you are talking about this glass of water, only this glass of water, then this glass of water will be termed as the system, and everything except this glass of water will be termed as the surrounding. So here you have a clear cut idea. Suppose you are going by train to a journey and you are sitting beside the window. So if you consider yourself as the system, so except you, all the other things in this universe will be termed as the surroundings. So there are actually two factors in thermodynamic parameter scenario. First one is the system, and the second one is the surroundings. A system is also part of the universe in which the observations actually are being made. So actually the difference between the system and the surroundings will be, both will be the part of the universe, but the amount or the area of the system will be much smaller in comparison to the area of the surroundings. And it is the system on which the observations will be made. But on surroundings, observations will not be made on primary focus. So the surroundings are actually involving everything other than the system. That's why it is written over here that in universe, the system and the surroundings, they come in total and make the universe. So for your better understanding, I've also brought up a picture which shows the system, surroundings, and the universe concept. You can see in this first picture, which is having a conical flask, which is having a liquid. Now this is the system, which is the blue colored part over here. It is system, and this is the entire universe that is actually defined over here. The entire universe is this box, parallelogram kind of box, and inside the box, which are having a conical flask, which is having some part of water. Now, in this case, if you take up this as the system, the labeled water, then except this, the entire thing, the box and the conical will be termed as the surroundings. So altogether, the system and the surroundings will make this universe. So here in the thermodynamic terms, I have come up with some basic points, which is the system in thermodynamics refers to that part of the universe in which observations are made, and the remaining universe constitutes the surroundings. So here, these parts are actually surroundings, and this one is the system. And the total of the system and surroundings make up the universe. So here, if we have started our basic understanding on thermodynamic terms, firstly we have come out to the very simple term, that is the system and the surroundings. But here some things are actually meant to known to, I mean the informations are to be given to you. Firstly, the entire universe, other than the system, is not affected by the changes taking place in the system. So you have to be very careful in understanding the fact. Suppose in this system part, some changes are actually being made, and that change will not hamper the surroundings. So the change in surrounding is independent of the change in the system. So therefore, for all the practical purposes, for all the situations that we will deal into, we will have the surroundings are that portion of the remaining universe which can interact with the system. So usually the region of space or what we are talking about is the neighborhood of the system that is constituted of the surroundings. If we even take up an example, so if we are studying the reaction between two substances, A and B, so we are dealing with the reaction between two substances A and B, and they are both are kept inside a beaker. So A is also inside this beaker and B is also inside this beaker. Now the beaker containing the reaction mixture is the system, and the room where the beaker is kept is the surroundings. So surroundings is what that can actually interact with the system. You can say if you are sitting over here and keeping a glass of water inside the glass, and you can take up the surroundings as a tree that is standing some 50 or 60 kilometers away from you. You see, the tree that is standing from 50 to 60 kilometers away from you is not interacting with the beaker at all. So that will not be part of the surrounding. Suppose you see here it is a beaker that is kept over here, and if we have a lamp post over here, or suppose this beaker is actually kept on the table, then classically speaking, both the table and this lamp post, which is actually standing far away, both are included in the surroundings part. But if you think carefully, having a bit of normal or common sense, and the lamppost is not actually interacting with the beaker, but the table is interacting. So the table, which is in its immediate vicinity, will be considered or termed as the surrounding. So here, I guess you have a very mild but a very clear also idea what is system and what are the surroundings. Now, the system may be defined by the physical boundaries, like beaker or test tube. Like here in this case, I have told you the beaker. Beaker is actually a glass, so the wall of the glass is actually having a physical boundary, like beaker or test tube. Or the system may be defined by a set of Cartesian coordinates to specify a particular volume in space. It is necessary, it is very, very important to think that all of the system that is just separated from the surroundings by some sort of wall, which can be real or it can be imaginary. So here we have a system and here we have surroundings. Now you tell me how will I differentiate between a system and a surrounding. So to see whether it is different from one another or to actually make these two things different or different by one another, we will have some physical boundary. Or if there is not a boundary, then a set of Cartesian coordinates which will have some specific volume in space that will be present. So it is necessary to think that all of the system is actually different from the surroundings by some sort of wall, which can be real or it can be imaginary. So in this case, you can see since the table is actually there, which is actually making a difference between the system or surrounding is imaginary wall or real wall. But the imaginary wall can also be there. Now the wall that is separating the system from the surrounding. Here we have a wall. Now this is a wall which can be real, which can be imaginary. So the difference or the separation between system and surroundings can be defined by a wall which is can be real or is imagination also. Now this wall is termed as boundary. Now this boundaries concept is actually introduced because it actually allows us or helps us to control or keep track of all the movements of the matter and energy in or out of the system. Here we have a system. Inside this, we have a matter and we have some sort of energy. Now, the concept of boundary or wall, introduction of concept of the boundary or wall allow us to control and keep the track, like what are the movements, whether energy is going out or coming in, whether matter is actually going out from the system or coming inside, or these aspects. So, in the concept of thermodynamic terms, system, surroundings, and the wall or boundary, which can be real or it can be imaginary, both can be actually present. So, depending upon the situation, we can assume what is the system, what are the surroundings, and the entire thing makes the universe. So here, a very trivial system that is should be known to you is the concept of universe, the surroundings, and the system. Basically, what I have told you over here, whenever we are having a system and we are having someone or something that is very, very far and which is having no kind of correlation with such kind of thing, that is actually termed as the surrounding. So here, when a lamppost or a tree which is standing far away from the system will not be included in the surroundings part, but which is the in the immediate vicinity, that will be termed as the surroundings. Now we have come up with a very classical examples of the systems. So further, these systems can also be classified according to the movement of energy and matter in or out of the system. So here we have three options. First one is the open system, second one is the closed system, and the last one is the isolated system. So we will first come up with the open system. So the name open system suggests the definition actually. So here you see it is the open system. In open system, if you have a look at this picture, you see this is the surroundings. The green portion is the surroundings, and inside we have a beaker which is having some amount of energy and matter, which is termed as system. Now in this system, you see the arrows are actually pointing towards both the system part and the surrounding part. The matter arrow is also will be coming to the system part and in the surroundings part. So heat and work, both, so energy, both can be coming in or going out from the open system. In an open system, there is an exchange of energy and matter between the system and the surroundings. This blue part is the system, and this green section is the surroundings. And you can see the content of the system is having an interconversion or which is getting exchange between the surrounding part. The matter is going out, matter is also coming inside. The energy in terms of heat and work can actually go out and they can go in. The presence of reactants in an open beaker is a classical example of an open system. We could have chosen only the reactants as system, then walls of the beakers will act as the boundary. So here, if we take up with a very classical example of a beaker, the beaker here is the system. So here you can see in this beaker, we have some kind of liquid, which is will be termed as my system. So these are actually termed by system. And when we will take up these only, so the molecules only as the systems, not the entire beaker as the system, then that is the reactant, then the wall of the beaker. So this portion, this, the wall, this will act as the boundary. This will be the boundary. This entire wall, the line that I am drawing on this blue line of the beaker, the wall of the beaker, it will be termed as the boundary, and it will be a real boundary because we are not imagining any boundary, but a physical boundary is present over there. Here, the boundary The presence of reactants in an open beaker is actually an example of an open system. Now, when we will take the entire beaker as the open system, then the boundary will be an imaginary surface enclosing the beaker and the reactants, but which is not the case over here. So here you have to be very careful in taking up that what can be done and what can be not, or what can be understood over here. The first thing is deciding of the boundary. What comes into your very first mind? We are talking about a beaker which is having some sort of reactants. Now, if we take up these reactants only as the system, then the wall of the beaker will be taken as the boundary. But if we can take up the reactants of the entire beaker will be an example, then the imaginary surface enclosing the beaker and the reactant will be taken up as the boundary. So you have to be very careful in choosing your system. Accordingly, the surroundings and the boundary will be decided. Next, we will come up in the part of the closed system. So what is in the open system? Just the opposite one will be in the closed system, but not necessarily the entire opposite. You see, in closed system, there is a lid over the beaker. So here matter is over there. So matter cannot escape. So matter cannot interact with the surrounding of the system, but the energy inside that can interact. In a closed system, there will be no exchange of matter. Matter inside the system will be fixed, but the exchange of energy is very, very feasible and possible between the reactants. Now, the presence of reactants in a closed vessel made of a conducting material. We have a conducting material, just like copper or steel. Suppose this beaker and these things are made of copper or steel. So copper and steel are standard conducting material. They are conductors. Since they are conductors, so the matter inside the system cannot go outside of the surrounding of the system that is surrounding, and something cannot come from the surrounding inside the system. So that actually makes it a closed system because no matter is getting transferred. But because of the conducting nature of the material, because copper and steel both are very efficient conductors, the energy inside the beaker can interact with the surrounding. So here, in the case of closed system like copper or steel, inside the example of a closed vessel or system, the energy cannot be interconvertible. So if instead of copper and steel, a non-conductor was present, this system would not be a closed system. Now we will come up with the definition of the isolated system. In an isolated system, there is neither an exchange of energy nor exchange of matter between the system and the surroundings. You see over here, in case of isolated system 2, the energy and matter cannot escape from the system and can interact with the surroundings. The energy and matter is inside. The energy of matter is actually inside of this uh, beaker, which is actually enclosed from top. Surroundings is over there, but since they are the material that is actually making up the system is non-conducting, in your daily life you might have undergone such kind of system where we call it as insulated systems. These are called the insulated systems. In kind of insulated system, you see there will be no exchange of energy and matter from the surrounding and the system. So this is just the opposite of the open system. In open system, we see there will be exchange of energy and matter between system and surrounding. In this case, the energy and matter both cannot, neither of them can be exchanged from surroundings to system and vice versa. So in case of a isolated system, energy exchange is not possible, matter exchange is also not possible. In case of closed system, matter exchange is not possible, but energy exchange can be possible. Energy exchange can be possible, but matter exchange is not possible. And also, in case of open system, the energy and matter both can be exchangeable. So if you see the definition, like you see the open system and isolated systems are just the opposite. In open system, energy and matter both can be exchanged between system and surroundings. But in case of isolated system, energy and neither energy nor matter can be exchanged. That is called as the isolated system. Here also, just like the other ones, I'll give you some classical examples. The reason is the thermoflask. Like in thermoflask, you might have seen in your house, in thermoflask, we actually make up some hot tea or drink and we or keep it inside. And for a very much longer amount of time, it remains hot or cold. So the energy loss does not occur inside of a thermoflask. Because in case of thermoflask, the walls are actually insulated. They are in an insulated system and closed. That's why neither the energy nor the matter can escape from the system, or nor the eye or the surroundings cannot also penetrate inside the system. So whenever we will put some very cold liquid kind of thing in thermoflask, it will remain cold for a very longer time. And whenever we will put some hot kind of system or hot drinks inside a thermoflask, it will remain hot for a very much longer amount of time. So this is the beauty of an isolated system. So presence of an insulated vessel is an example of an isolated system. So before going to the very deep connection of this second part of this chapter, we will first see how this can be done. So firstly, we will remove these all these things. Yep. Now there now we have talked about three different kind of systems. First one is the open system. Suppose a pot of boiling water. This is an open system because a burner in beneath the pot that is having the boiling water is an open system because a burner is supplying energy in front of heat and the matter in the form of water as the water boils. So if we are having a pot of boiling water, here I am actually giving you some very daily life examples of open system so that you can connect with this very easily. So we are having a pot of boiling water and beneath we are having this fire. A pot of boiling water is over here, which is actually producing a heat. A burner is actually supplying energy. This is the burner, which is supplying heat energy. And this is the boiling water, which is getting evaporated. So both the matter and energy is getting exchanged. Here you can see this is the matter. Matter is this boiling water and energy, which is this transferred heat from the burner. This is an example of an open system. A closed system can exchange energy but not the matter in thermodynamics. The sealed pouch of a ready-made dinner that is dropped into a pot of boiling water is a closed system because thermal energy is transferred to the system from the boiling water, but no matter is exchanged. Suppose we are having a very big container which is having a large amount of boiling water. So actually, the heat energy is stored inside the water, and suddenly a pouch packet like this is dropped into the a pouched pack is dropped inside the bowl or the vessel. Now, in this vessel, you see the matter inside this pouch is not getting exchanged with the boiling water unless the pouch is actually leaking. And then the energy, the thermal energy that is contained inside the boiling water is getting transferred and exchanged with the pouch packet. So in this case, you see the energy is getting transferred or exchanged, but the matter is not. So this is a classical example of a closed system. And lastly, we are having an isolated system. But here I will take you, I've already given you a very good example of isolated system, which is a thermoflask. But I will tell you the truth. A truly isolated system cannot actually exist. An insulated thermoflask, which is having some amount of hot coffee or tea inside, is approximately an isolated system. But entirely an isolated system cannot be there. In all cases, the amount of heat that is lost by the system is equal to the amount of heat gained by the surrounding. So the amount of heat the system is having, or actually system is actually having some amount of heat it is releasing by the system, the same amount of heat is actually gained by the surrounding, which is very much trivial because the total energy of a system plus its surroundings is constant, which must be true if energy of conserved. So the energy for the energy to be conserved over here, we must see the total energy of the system and the surroundings would remains constant. As I have said, in an insulated thermoflask, which is containing hot coffee, is approximately an isolated system, not entirely an isolated system. But eventually, when the coffee cools, as the heat is actually getting transferred, but the process is very, very slow. And in all the cases, the thing that I have mentioned over here, the amount of heat that is released from the system is equal to the amount of heat gained by the surrounding. Or in opposite term, the amount of heat released by the surroundings is actually equal to the amount of heat taken by the surrounding. The total energy of the system plus the surroundings is always constant. So, because we know the energy cannot be created and not be destroyed. So, the energy should be conserved. You have read in the energy of conservation of energy law, or in the conservation of momentum law also, total energy of the universe must remain constant. We cannot create energy or nor we cannot destroy it. So, with this basic understanding of the system, some basic thermodynamic parameters, here we will draw an end to our lecture 1 of the thermodynamics. In the next consequent part, we'll be discussing a bit on the lecture 2, where we will see how the states of a system is defined and which is will define the complete description of a system. So in that section, we will see how the states or the state function, or you can say the state variables are involved. The state variables are very important parameters to give a complete description of the system, which includes temperature, pressure, volume, and many other aspects that we will be discussing